Hi everyone, and welcome to our webinar, which is introducing Peregrine V6 features and applications. I'm Tom Pritchard, and I'm the Peregrine product manager. I'll be introducing you shortly to our other speaker today, who is Matthew Gilbert, the MD here at LimitState. Just a quick overview of what we will be covering today. Firstly, Matthew will be talking about the benefits of structural optimization, and then I'll jump into doing some practical things involving the applications of Peregrine V6, specifically around holistic conceptual design of buildings, structures including cables, stabilization of optimization structures, and also ensuring symmetry in the design that you're coming up with. Then there'll be a brief summary, and hopefully at the end we'll have time for maybe one or two questions in a Q&A. So without further ado, what I'd like to do now is just pass you over to Matthew, who'll be talking about the benefits of structural optimization.
Thanks very much, Tom, and thanks very much everyone for joining us for this webinar today. I'm just going to say a few words just to kick things off on the benefits of structural optimization, and then I'll hand straight over to Tom, who will give the meat of the webinar. Okay, so what are the benefits? Well, there are many benefits. It depends what your objective is, but one of the most pressing objectives at the current time, as many of you will be aware, is getting more from the same amount of materials. In other words, designing structures that consume far lower amounts of material. And in the construction sector, we know this is a huge problem. Concrete and steel, and to a lesser extent other materials such as aluminium, are widely used in construction, but are responsible for a significant proportion of total CO2 emissions. So we've got a huge opportunity to make a difference there. Now, the most obvious thing to do is to build less frequently, new buildings and other structures. Also reuse structures much more than we are doing at the moment. But sometimes we do need to construct new buildings and other structures, and in that case, it makes sense to use optimization to get the most possible value or benefit from any given volume of material. And in particular, for a number of years now, we've been focusing on layout optimization, and this is something that's perhaps less widely understood than some other forms of optimization, such as size optimization, but layout can be really, really important. Just got a truss example on screen now. I've got a standard Pratt truss design at the top, and then we've got an optimized design below. And actually, the optimized design consumes 40% less material than the more traditional truss above for the same deflection limit. So, you know, almost 50% reduction in material just by changing the geometry. In addition to trusses, there are many other aspects of the structure that we might be interested in. So, for example, in buildings, we use beams and arrangements of typically of orthogonal beams forming the floor plate, but we can use optimization to show that we can significantly reduce the amount of material if we're prepared to move to different layouts. So on screen now, we've got a sort of square grillage with orthogonal beams, and we're using prismatic beams in this case. If we move to using a different layout and also tapered beams, then we can have a 74% reduction in the amount of volume of material required to construct that floor plate. So very, very significant reductions are possible. In an attempt to sort of spread the message, so to speak, we have been involved in making available some web tools in association with colleagues at the University of Sheffield and a couple of companies, Arup in the case of the truss layout optimization tool that you can access at layup.com, and Curvies in the case of the bridge layout optimization tool. But if you're unfamiliar with layout optimization, this is a really good way of getting started, having a play around on your PC or on a tablet or on your smartphone, and see what the influence of loads and supports are on the optimal form. And then Peregrine, the subject obviously of today's webinar, really just pushes that further, moving from 2D to 3D and allowing far more flexibility in the setting up of the problem, and also in the sort of post-processing tools that we can apply. And that's really what Tom's going to be talking about shortly. It's not been out long. We're starting to see examples of structures being fabricated that have been designed using Peregrine, but we hope in the future there'll be many more. And that's, I guess, largely down to you people on the webinar and others. Okay, so just hand over to Tom, who will pick up on Peregrine version 6.
Thanks, Matthew. So let's take a look at the applications and the new features that are involved in Peregrine version 6. Firstly though, a little bit about the workflow that's involved in undertaking a Peregrine optimization. We start off by defining the problem, then looking at optimization. Third step is post-processing, and then fourth, the output. The problem definition, looking at things like the design domain geometry, the properties, supports and loading, and also the material properties that are involved. We then go on to stage of optimization. First we perform a layout optimization, and then looking at post-processing, so things like geometry optimization, stabilization and such like. And then finally we look at the output, so we have the display and the structural details. And putting them all together, it looks something a little like this. So let's go over the new features. First we're going to look at holistic building design, including beam grillages, then tools for the design of cable supported structures such as bridges and stadiums, then load and support mirroring, and finally global stabilization of the structures. So first up we'll take a look at grillages and holistic building design. And that comes under the definition of the problem stage of the workflow that we were looking at previously. On the right here you can see we have a design domain component which allows us to select between truss and grillage type structures, and then feeding into that we have this I-beam cross section. Similarly, we can also specify CHS, and we can change the domain type to be a truss for if we're looking at, for instance, walls or more traditional frame type structures. And it's useful to optimize trusses, columns and floor plates simultaneously, and the groundwork for that was undertaken by Dr. Lin Wei-He as part of the development of a previous technology preview version of Peregrine itself, and effectively having the floors plus the truss bracing and the grillages all together is this holistic design. And the example we're going to look at here is a very simple one of 10 floors with gravity loading on them and 4 wind loaded directions, so one for each face. And when we look at the sort of fully unencumbered optimization, we can see we have a reference design, a reference weight of 100%, and this interesting Mitchell type cross bracing. But when we reduce that down and constrain it to being simply just 4 columns and cross bracing, the weight is actually 3 times greater than that. Okay, so we're going to take a very similar problem here in Peregrine, and we can see here we have the problem geometry, loading, material properties, supports, all feeding in to our design domain and our problem specification. If we zoom in a little closer to the design domain, we can see that we have 2 components here, one for the grillages and one for the cross bracing on the walls. And feeding into that, if we come down here a second, we have CHS for the walls and I-beams for the grillages. Here on the right we can see different views of our problem setup, so just from one side, the top, and then a perspective view. If we come now to solve it, It'll take a little while to run through because there's 5 different load cases, obviously the floor loading and the wind loading on each of the different faces, but it shouldn't take too long to actually come up with a solution for us. And while it's doing that, if we have a look here, we can see actually that we have supports all the way around the edges, and that's reflected here in these images as well. And now it's solved. It'll take a couple of seconds just to come through and render within each of the different viewports, but while that's happening we can see here that our output, we've set that to be 100% of the volume, so we can compare any changes that we make to this. And from above we can see our grillage layout, which is quite an interesting cross pattern in the middle with each of the 4 corners. From one of the sides we can see our bracing pattern, and it's a little different to what Linway had found in his studies, but the problem setup is slightly different as well, I guess. But we have cross bracing combined with vertical columns and also this Mitchell truss, so all 3 different types of bracing combined in one particular problem, and then perspective view on the right here. So one of the interesting things we can do is just change some of the different inputs into our problem. So what I'm going to do is just change the number of columns that we have at the bottom here, change the number of supports that we have at the bottom here by changing this support spacing. So if I change that from 1 to 10, it'll run through again and we should get a slightly different solution. Okay, now that's run through. Again, it'll take a little time to render, and then we can check the solution and also what the volume change has been. So on the right here we can see in our Rhino previews that the grillage layout has changed quite dramatically, and similarly the view from the side, the bracing has changed. It's actually quite a lot more simple now, and it's the same repeated pattern up each floor. So let's have a quick look and see what the change to the volume is. If we look here now, so actually we've only added 10% to our volume by restricting the support positions on that bottom floor to the corners. And that's just a quick look at what we can do using our holistic building optimization. But obviously you can also put in more complex problems than that. So this is one of the example files that get distributed with the software, and here you can see there's various shapes of floor plate and tower configurations within this. So moving on, we're going to take a look at cable supported structures and how they are dealt with in Peregrine version 6. And this is an area where users felt that value could be added into the software in the conceptual design of long span structures. And it builds on work that's been undertaken by Dr. Helen Fairclough and a number of others, published in the Royal Society in 2018. The name of the paper is there for you to take a look at it if you wish. So how do we deal with self-weight, and what does that have to do with the cable supported structures? So the basic self-weight in the software is assuming that the weight of any element is lumped at the node, so that neglects bending. And what Dr. Fairclough did is examine the implementation of catenary members in the optimization by defining them as carrying axial stresses only under a combination of axial force and self-weight. Alongside that, obviously, there needs to be some acceptance of bending, so there's also implemented a rigid or pinned jointed beam elements that had bending strength within them. And this figure here is actually part of the paper that Dr. Fairclough published, and we can see a range of different types of optimum long span structure, going from A, which is a very simple hanger type cable stay bridge arrangement, through to H, which is a very complex optimized structure. And effectively what we're looking at here, say we take a span of 2.5 kilometers, we can see that for the type of structure that we would get with A, so our traditionally designed and built structure, then the volume is up here around 2.5. But as we move around and towards H, that volume reduces quite significantly down to maybe 0.5, 0.7, something like that. So maybe 3 or 4 times lower volume the further around these designs we go. And somewhere in the middle there's going to be an optimized design which is both much lower weight than the hand designed solution, but also eminently buildable. And how is it all implemented in Peregrine? So if we take a look here, again it's part of the problem definition, and in this case we're looking at the material components. So on the left hand side here we have our traditional material component, which takes tensile and compressive stress limits, and our self-weight model is defined as being lumped. On the right hand side here we can see, however, that we've defined a catenary member, catenary self-weight model, and for that we can allow a tensile stress, in this case of 1500, but importantly 0 compressive stress, and then we can provide those to the software in order to choose between the two of them to decide which one is going to be present in particular places within the optimized structure. So let's take a look at the implementation in Peregrine, and here we're going to look at a long span cable stayed bridge example with a 4 kilometer span and a height of 1 kilometer. So you actually have a 1:4 rise to span ratio. You can see our Rhino preview here at the bottom right hand corner with the rectangle for the design domain. We also have supports and loading conditions. But the important thing that we're going to look at here are the two types of self-weight model and the materials that they're applied to. So here, if I zoom in, we can see we have our cables, our material component, and we've selected the catenary self-weight model and applied a tensile stress limit of 1000. On the right here we have our beams, and they're using a pin beam self-weight model, and we've provided those with equal tensile and compressive limits of 350. If we scroll across, we can solve, and in just a couple of seconds we get our solution here, and we can see that it's very much a similar structure to the sort of thing that we were seeing in the work of Fairclough, but obviously here actually we're looking at multiple load case formulation, whereas Fairclough and co-workers were looking at a single load case formulation. So that's one of the improvements that we've put into Peregrine. So let's see what happens when we change, for instance, the tensile strength of the structure, make it twice as high. First, let's just take a quick note of the volume, so 8.058. If we change that tension value to 2000, very quickly it will solve again, and now we can see that we're actually getting quite an interesting practical or more practical structure where we have a tree with 2 arms. But what's the effect on the volume? We can see here actually it's gone up to, or gone down even, sorry, to 5.177, so a 35% reduction in volume for a more practical structure while still being much more efficient than a single pylon solution. And then finally, let's have a quick look to see what happens if we reduce the span to rise, so that we're actually going to 0.5 high rather than 1 kilometer. It's taking a little while to solve, but again a more tree-like structure. And let's have a quick look at what the change in volume is for this. So now we've gone up slightly to 5.43, so a 5% increase in volume over our previous solution. So it's interesting that we're not actually increasing it by a considerable amount, but we can see that the structure now wants to make more use of these compressive arms now that the design domain has been made shorter. And just going back to the presentation, we can see actually that it's not just long span structures that we can use this catenary element in, it's actually also things such as stadium roofs, where we can see on the left hand side here one type of structure, whereas on the right, when we're using catenary elements, we're getting an entirely different optimized structural form. So the third thing we're going to look at is load and support mirroring within the software. And mirroring promotes a symmetrical structure as the solution, and effectively it allows us twice the problem complexity for the same computational effort. So there's a number of reasons why you might want to use it. And within Peregrine there are 3 modes. So the default is having the load on one side, but the supports are mirrored and the solution is found to be symmetrical. So the optimizer goes through and looks at the best symmetrical structure for carrying those loads on that one side. There's also simultaneous, where both the loads and the supports are mirrored in our mirror plane. And thirdly, there is an antisymmetric mirroring option, which allows the loads and the supports to be mirrored in position, but the direction of the load is unaltered. Again, mirroring is something that is set up in the problem definition, and we can see here within the mirror component that we've in this case chosen a symmetric mirroring type, and we've applied that to the mirror input into a point load. You can also do the same into the line loading, and the supports will be mirrored by default should you provide a mirror plane into the problem specification, as we can see on the right hand side here. In this particular case we've just set a YZ plane and put that in at the origin, but you can suggest the point and the plane and the direction of that mirror as you need to. As a brief example, what we're going to look at is one taken from real life, and in this case one that's been talked about again by Fairclough et al. In a good article in the Structural Engineer. The example is one of a large basement level transfer truss in a multi-story building, and we can see it has a 50-meter span and a 12-meter depth, and there's vertical support provided at each side from diaphragm walls, and there's a number of point loads that are applied at the top and the bottom of the design domain, some of which are very large in magnitude. And as the paper explains, the manual design solution that we can see at the bottom here is one that resembles something like a Warren truss, which links all of the load points and has a weight of over 460 tons. If we look at the fully optimized structure, then we can see that we can get something that is 57% lighter than this manual structure, so just over 200 tons, but obviously the complexity of that is far greater than the one that you come up with by hand. So if you look at an optimized and also simplified structure, then we get this one that we can see at the bottom here, which is actually 51% lighter than this, so not actually that much different from the fully optimized structure at the top right there, but considerably easier to construct. So let's take a quick look at a mirroring example in Peregrine. So here I recreated the problem with the initial setup taking not much longer than about 30 minutes, and the thing to notice is that the problem is symmetrical about this center line here on the vertical axis, and that allows us to take advantage of the mirror functionality. Essentially all I did was set up one half of the problem, so one half of the design domain, one half of the supports, and one half of the loading, and you can see here in light blue on the right hand side the supports and the loading are mirrored, and what's going to happen is that we're going to get an optimized structure in this half that will then be reflected about that center line. So if we just have a quick zoom in, We can see here I've set up the mirror plane as a YZ plane feeding into our problem specification. And if we take a look at the loading, we have loading along the top chord, which I've set as being symmetric for the mirror, and then loading along the bottom chord, which I've also set as being symmetric. If we solve this problem, oh, you evil bugger. If we solve this problem, we can see that it will run through relatively quickly, and the solution that we find will be very much like the complex one that was found by Fairclough in her paper in the Structural Engineer. So we can see that the mirroring is actually allowing quite a quick solve and ensuring that whatever we do, we're resulting with a symmetrical structure. So let's take a quick look at the volume. This is actually the percentage volume difference between this and our benchmark, so here effectively 0. It's still very complex, so what we can also do is reduce the complexity of the problem in order to see what effect that will have. So if I come here, we can see we've got a slider for that. Let's reduce the complexity, and it's solved almost immediately. But what effect does that have on the volume? We can see here that this is actually a percentage volume difference from the benchmark, and it's gone up by just over 0.4%. Again, still quite complex though, so let's see what else we can do within the software in order to make that a little bit better. First, I'll just reduce that down a little so we can see what's going on. So the first thing we may want to do is actually undertake a geometry optimization, and that's going to move all of these nodal positions to slightly more advantageous positions, because the initial layout optimization was actually using a set nodal positioning. And if I scroll over to the right here, we can see the difference between the two. So this is our original solution on the left hand side, our original simpler solution, and on the right hand side we can see the one that's the result of the geometry optimization. And actually the difference in volume between this solution, the geometry optimized one, and the benchmark is almost nothing. So we're pretty much the same volume here as we were when we were using this nodal complexity of 30 to start with. So the next thing we might want to do is actually simplify this structure even more. So if I connect the output from the geometry optimization and feed that into the simplify component, what it's going to do is it's going to try and reduce the overall complexity of that problem, or of that solution, sorry, whilst remaining within a specified allowable volume increase. And in this case I've actually set the volume increase limit to 50%, but actually we can see that the volume's only gone up by 0.6% from this in order to create a much more simple structure. And again, comparing the volume of this to our benchmark, we can see that it's actually gone up by 1% over and above that very complex benchmark solution that we got when we were looking at a solution involving a complexity of 30. So this is much more eminently buildable than the ones that we've come up with before, and the solution has been made a lot quicker to obtain by using this mirror functionality. And the last thing we're going to look at is structural stabilization. So stabilization within Peregrine uses a semi-definite programming method to ensure that the structure is linearly stable under the specified loading, and it examines buckling modes and identifies the critical members within those buckling modes, and then resizes or adds members to the structure in order to suppress buckling up to the desired level. And as later stages, such as geometry optimization, may reintroduce unstable equilibrium, this is generally what we recommend to be the last stage in the workflow. And within Peregrine, the stabilization comes in as a post-process function, and we can see we have the output from a layout optimization that goes into the stabilize component, and we add our load factor, in this case 10, into that stabilized component, and we can see what the volume is, and then output from that into, in this case, the view component to see what that solution looks like. In Peregrine, we're just going to take a look at an example that actually is quite basic but is distributed along with the software to give people a better idea of how it works, and that's one of a half wheel, as we would call it. And we can see here on the right, our design domain is at a basic square. On the left hand side we have a fixed pin, and on the right hand side we have a roller pin support. Midway between the two of those we have this vertical load, although we can, if we want, move the position of that load there. If we come in and solve, as it's so basic, it solves very quickly, and we can see we get this nice half bicycle wheel solution. Again, if we wanted to, we can move our load around and very quickly get the optimum solution for the different load positions. But that's not actually what we're looking at in this particular case. What we're going to look at is how we provide stability for this. So if I turn off the display of the design domain behind the scenes, we can see that actually there's no connection between our support here and our load there. So it's actually in unstable equilibrium. So what we're hoping with stabilization is that we can prevent that from happening. So we've got the stabilized component on our canvas already. We can see we've applied a load factor of 1 to it, but nothing's actually happened. What we actually need to do is connect up the output from our layout optimization into the stabilization. It hasn't actually disappeared. What's happened now is that we actually have a gallery view where on the left hand side we can see our original half bicycle wheel solution, and on the right hand side we can see our stabilized solution. And actually the volume has only increased marginally, so virtually nothing at all. But we've got these slender supporting members that are preventing instability from occurring. What we might want to do is increase that load factor to something more credible. So let's put 20 in, and we can see here that now the size of these support members has increased, and actually we've also got another couple of extra members that have been added into the problem. And finally, if we ramp that right up to 50, we get a reasonable change in the optimum form itself, and that's because the members that are being put in order to provide the stability are roughly the same cross-sectional area as the original elements in this structure. So it's actually using both of those in combination with each other to carry that load, rather than stabilizing with small elements. It's using the stabilization members as part of the actual load carrying structure as well. And obviously that was a very simple example, but what we do find is that quite often in optimization we get these types of problem and these types of solution where we have two planar structures next to each other where they're obviously in unstable equilibrium and should realistically be supporting each other in some way. And when we put stabilization on, we get some solution that looks more like this on the right hand side here. So we have cross bracing between those two planar structures in order to provide further stability. So that brings us to the end of the webinar section. We'll have maybe some Q&A in a second, but just to summarize, the climate emergency is demanding that structural engineers do more with less material, which is where optimization can be a big help. Peregrine version 6 allows engineers to apply layout optimization techniques to a far wider range of conceptual design problems, and you can download it from Food for Rhino. It will come with a 14-day trial of the full functionality, and there are various licensing options available once that 14 days are up, including free academic licenses, the details of which are explained within the software itself. And just to reiterate that layout.com and layout.com/bridges are both available as free web apps for people to use and get used to layout optimization in general. So I know we've run a little bit over, but there may be some time for Q&A. So I'll just turn my video back on. And Matthew is also here. And
we just had a question, Tom,
okay,
on the chat about exporting volumes of different materials. So I just confirmed that that's possible. You can extract, for example, the volume of cables and the volume of, for example, structural steel.
Yeah.
And that's no problem. For any other final questions before we finish, then please use the Q&A functionality as an open one here. Is it possible to add fixed strut clamped supports? I think that's a good question. So for trusses, there is no benefit in doing that because we have pin joints. There is a benefit in the case of grillages. The moment you would need to actually have a kind of a little line of pin supports to replicate a fixed support. That's my understanding, Tom.
Yeah, absolutely. That would be the way to do it.
Yeah, I think in the future we will probably make that available as a support type for Stephen.
Okay, well, we're a little bit over time, so thank you for staying with us, and hopefully we've answered all your questions. If you do have any more that come as a result of this webinar, then please do feel free to just email us on info@limitstate.com, and we will be more than happy to answer any questions that you do have about the software. So finally, I'd just like to say thank you all for coming. Thank you to Matthew for being part of the webinar, and please do look out for other webinar notifications that we'll be sending out later in the year and in the new year. So thanks very much. Goodbye.